I think since I just gave y'all that Henry's Law formula, I think y'all can work that without me. I think y'all can plug numbers in and work that. And tell me what you get. I only set you up for 2 significant figures on this. I just copied a problem out of the book. Do y'all get 0.16 molarity or moles per liter for the answer? 0.16. So if we're calculating the concentration, the Henry's Law constant is 3.1 times 10 to the minus 2 moles per liter times atmospheres. And the partial pressure of CO2 is 5 atmospheres. So the concentration of the CO2 in this soft drink, while it's canned, is 0.16 moles per liter. Okay, that's in the bottle. That's how much carbon dioxide is dissolved in solution. Now, let's add a B part to this. Because y'all, when we open the soft drink, what are we doing? We're just exposing it to atmospheric pressure, right? And now we know, what's atmospheric pressure? Do y'all know what atmospheric pressure is? Pressure of the atmosphere. Yeah, but do y'all know the quantitative number for it? How many ATM it is? 1. We're at 1 atmosphere, okay? But when you do the calculation, you're not going to use the pressure of 1 atmosphere, because do y'all see that the pressure you use, it has to be the partial pressure of the CO2, okay? So once you open the soft drink, there's a very small percentage of CO2 in the air. So once opened, the partial pressure of CO2, that's what that's saying, is 0.0004 atmospheres. So let's calculate what concentration remains dissolved when the partial pressure drops that much. Do y'all get that? 0.031 times, I guess it's really 1.2, isn't it? Thank you. 1.2 times 10 to the minus 5? I mean, that explains why your soft drink goes flat after it's opened. As it remains open, the CO2 bubbles out. Okay? Any questions on that? All right. Next section. This is section 13.5 in your book, Colligative Properties. Colligative properties are properties that depend on the number of solute particles in solution regardless of their nature. There are 4 colligative properties. They are vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. There is a formula that fits in with each of these, and I'm going to write the formulas out beside them. Vapor pressure lowering's formula is P1 is equal to X1 times P1 standard. Freezing point depression formula is delta TF is equal to KF times M. Boiling point elevation formula is delta TB is equal to KB times M. And osmotic pressure looks like this. That's the symbol for pi equals MRT, but it doesn't stand for pi. And I'll explain what all those mean. Delta T and KB and everything. Ma'am? That is a cursive M. What's a cursive M? She's asking about this. That's going to be malleolate. All right, what is a vapor pressure, y'all? Do y'all remember us talking about it? Wasn't that one of the questions you asked a second ago about vapor pressure? So look, here's what a vapor pressure is. Like if we're looking at this bottle, which is empty still, if it had acetone in it, then some of that acetone is going to evaporate and be in the gas phase above the solution, and it exerts a vapor pressure. And what Alexandria was asking about earlier in class, because I think she's been studying for her test, and she realized, am I right? She realized she had vapor pressure, but she didn't have a whole lot of stuff written about it. Fair? So if you have really strong intermolecular forces, then does it make sense to y'all that solution wants to stay in the liquid phase, right? But if the intermolecular forces are weak, then it would more readily evaporate. Therefore, weak intermolecular forces is going to have a higher vapor pressure. Well, some substances, the vapor, they have flammable vapors or harmful vapors, and so we want to control the vapor pressure. We want to keep them from evaporating, especially if we're talking about like an industry. And we've all driven down the road and seen an industry that has those huge columns of stuff. Okay, if there's chemicals stored in there, you want to lower the vapor pressure for many safety reasons. And what this colligative property says is that, y'all, the P1 stands for the vapor pressure of the solvent. I should write this and not just talk it. P1 stands for the vapor pressure of the solvent in solution. Catch those terms. Solvent in solution. Have we talked about X and what X means? Did we do any calculations with X? Yes, so we did do that? We talked about mole fraction? Okay. X1 is a mole fraction, so it's the moles of the solvent divided by the total moles of the solution. And then P1 standard is talking about the vapor pressure of the pure solvent. And I want to point out to y'all something in this formula. Notice how everything in the formula is labeled with a 1, right? Y'all, everything's about the solvent. Okay? I'm pointing that out because think about it. When we do molarity, isn't molarity solute over solution? And isn't molality solute over kilogram of solvent? Usually we're looking at the solute over something, but look at this. It's the solvent mole fraction, okay, over the solution. So, look at number 1 on your sheet that I just gave you on this worksheet. How are you going to go about solving that? Okay. What you going to plug in? Okay, water's a solvent. We're talking about putting glycerin in water, right? So do you guys all agree that with that formula, we are trying to calculate P1? X1 means we need the moles of glycerin. Nope. We need the moles of water. I just did what I told y'all not to do. Divided by the moles of water plus the moles of glycerin. And then the P1 standard is 23.8 millimeters of mercury. The gist of this problem is calculating the mole fraction, isn't it? Where are you going to get the moles of water from? Okay, if we have 500 milliliters of water, what's the density of water? 1 gram per milliliter. So if we have 500 milliliters of water, that means we have 500 grams of water. And then I just convert that to moles. .75 moles of water.
You converted the water from milliliters to grams, just like a 1-to-1 ratio.
Yes, what I really did is I said that mass is equal to the density times the volume. The density is 1 gram per mil, and the volume is 500 mils. So that's 500 grams. So we needed that explanation because, y'all, we have to do the same thing for glycerin. How much glycerin do we have?
50 milliliters.
We've got 50 milliliters of glycerin. $50 milliliters of glycerin does not weigh 50 grams because the density of glycerin, it tells us in the problem, it's 1.26 grams per mil. So 50 milliliters of glycerin would have a mass of what? 63 grams. Then I have to convert that to moles. And you're given the formula on the sheet, so you can do the molar mass. What do y'all get for molar mass?
You get 168.
For molar mass or for
Molar
moles? Okay,
mass,
okay.
92.11.
Yeah. Yeah, 92.11 grams per mole for the molar mass, and so I got that to 0.684 moles of glycerin. So take that information and calculate the mole fraction of water, because water's the solvent. Shucks. Mole fraction, 0.976. Is that what y'all have? Okay. Remember, or I'll remind you, mole fractions are unitless, so the value of x is simply 0.976. So P1 is equal to X1 times P1 standard. P1 is equal to 0.976 times the 23.8 millimeters of mercury. Do y'all get 23.2?
Good.
Okay. Do you see the numbers agree with vapor pressure lowering? Because the problem tells us that pure water at this temperature would have a vapor pressure of 23.8. If we dissolve glycerin in the water, then we've lowered the vapor pressure to 23.2. Okay, that's the new vapor pressure, we've calculated it. And that's vapor pressure lowering. Okay? What's the next colligative property that I gave you as on the list? Freezing point depression. Okay? Let's take freezing point depression and boiling point elevation and let's do those together. Because y'all can tell from their formula that the formula looks very similar. Okay, what does that triangle in front of T mean? Change in. Y'all notice what we just calculated on that vapor pressure one, we calculated the vapor pressure. If I were to ask you how much did we lower the vapor pressure by, how would you figure that out? You would find the difference. Okay, we actually calculated the vapor pressure. On this one, you're going to calculate the difference. You're not calculating the temperature that it boils at or the temperature that it freezes at. You're calculating how much you change it by, typically.
Which one was the one you said? This is the freezing point?
This is the freezing point depression and the boiling point elevation. Yes. So the delta T is the change in freezing temperature or freezing point, or it's the change in boiling point, depending on which one you're looking at. Okay? Delta T is the change. The K is called a Malal boiling point constant or a Malal freezing point constant, depending on which one you're calculating. And as y'all asked earlier, y'all said, is that M cursive? And it was, and you guys told me that the M means the molality. Okay, so let's look at number 2. Automobile antifreeze consists of ethylene glycol, which is C2H6O2. It's antifreeze. Calculate the boiling point and the freezing point of a 25% by mass solution of ethylene glycol in water. What does 25% mean?
25% of solutions.
It means 25% of the solution's antifreeze? What were you saying?
It'd be 25 grams ethylene glycol over 100 grams of.
It means 25 grams of ethylene glycol over 100 grams of solution. Because percent is part divided by the whole. We are asked to calculate 2 things in this problem. We're asked to calculate the boiling point and the freezing point. We're going to do boiling point first. So boiling point is going to be delta TB is equal to KB times M. KB, you would look it up on this table. You don't memorize them, y'all, you look them up. There's a table for you to look them up on. So tell me, which KB are we using? You said 0.52 with a question. You said 0.52? How do you know which one to use?
Water.
Yeah, it says it's in water. So you were right. It's the 0.52 is your KB. You have to look it up based on your solvent. Okay? The units were degrees Celsius per molality. I don't know if I left the table up there long enough, but that's the units. Tell me what molality means. It means moles of solute over kilograms of solvent. So instead of writing on this thing solute and solvent, I want to write what it is. What's the solute here? Ethylene glycol antifreeze, yeah. So it's moles of ethylene glycol over, what's the solvent?
Water.
Water. We don't have the molality. What are we going to need to do to calculate the molality? We're going to have to take the grams to moles for the ethylene glycol first. I got 62.08 for my molar mass. Is that what y'all have? Did you say no, that's not what you got?
Yeah.
62.08? Okay. So from, are we together? Moles is .4027?
So this was for the, is this for the freezing or the boiling? Cause like you wrote both the equations up there and I was a little confused.
Well, we're gonna work boiling first. Yeah. Can y'all tell me what to do next?
You gotta do, the grams of water to kilograms.
Okay, so do y'all agree that, I know my moles of my malally, I know this. So my top number here is gonna be 0.4027 moles of ethylene glycol. It's gotta be over kilograms of water. How much water do I have in this 25% solution? 75 grams. Where'd 75 come from?
You have 100 grams solution, 25 of ethanol.
That's right, we got 100 grams of solution, 25 of the ethylene glycol, so 75's water. How many kilograms is that?
0.075.
0.075 kilograms of water. So what's the molality? .37, is that what y'all have, malal? Okay, boiling points first. Delta TB is equal to KB times M. We're solving for our change. What's KB? We looked that up earlier. 0.52, yeah. The molality is 5.37. What do y'all get? 2.79 degrees Celsius for the delta TB. Any questions so far? We're not finished with that, but any questions? Anything at this point? What did I ask y'all to calculate on that question? It said calculate the boiling point and the freezing point, but we've been working on boiling point. Is this the boiling point, 2.79? No, that's the change. What's the boiling point? It's boiling point elevation is the property. So water normally boils at 100 degrees Celsius. We have elevated the boiling point by 2.79 degrees Celsius because it's boiling point elevation. So now this water will not boil until it reaches 102.79 degrees Celsius. This is what I was telling y'all in the previous one. We calculated the new vapor pressure. But in this, when you're doing boiling point and freezing point, you're calculating the change. You're not calculating the new temperature. Does that make sense on boiling point? Okay, now I'm going to scroll. Y'all got to do the other half of the problem. You've got to calculate the freezing point, and here's the table where you get your information from. So y'all calculate the freezing point of this solution. How's it coming? Do you have an answer? It's two different questions. How's it coming? Thumbs up, all right. Do you have an answer? Another thumbs up. Is your change in freezing point, did y'all get 9.99 degrees Celsius for the change? Okay, I'm getting 2 affirmative head nods, and you're looking at me like that little dog, that little emoji that I love.
You said 9.99.
9.99, okay. All right, so let's work. I'm gonna get off this table, assuming that y'all have everything you need from it. Delta TF is equal to KF times M. Y'all got the KF from the table, 1.86 degrees Celsius per molal. Agreed? Okay?
Can I see the table again? I think I used the wrong number.
Okay.
Oh, golly. I think you.
It's a lot of numbers up there.
Yeah, I used 0 degrees Celsius.
Oh. Okay, that's okay, Devin, but please tell me you did not punch it in your calculator.
No, I
Right,
didn't.
okay, 'cause that's what
I looked at that table and I
I
said.
know, I'm
and
recording
and I
myself.
wrote 0 on my paper.
But y'all, when I'm gonna tell you, when I'm with somebody working and they're like, okay, so it's 0 times 5.37. Well, I just got 0. Y'all, what would you do if you saw somebody do that? Okay. Okay, so that's why you were done so quick, right,
Yeah.
Debbie? Like, this is it.
Okay, yeah, I
Okay.
got what y'all got.
Okay. 5.37 molal. Delta TF, what'd we say? Because I typed in the times 0 in mine. 9.99, essentially. Okay. Now, what do? We want to know the freezing point. And it was on that chart, but y'all don't need to look that up. What temperature, Devin, does water normally freeze at?
0 degrees.
0. Y'all, freezing point depression means we've got to subtract this number from 0. And I'm accenting that because sometimes I work this problem in water and people mistakenly think, oh, it's just the answer negative, but it's not. We've subtracted it from 0. So now this solution, it's going to have to drop to almost 10 degrees, negative 10 degrees Celsius in order to freeze. Make sense? Can y'all think of a practical application, well, besides putting antifreeze in your radiator? Okay, besides that one, because that is a practical reason of not wanting the solution in the radiator to freeze or boil. Can you think of another example? In life, because look, we deal with water a lot, because water is everywhere in life. Of where we add stuff to water to either lower its freezing point,
Like salting the roads.
like salting the roads. Yes, salting the roads. When we hear of bad weather, freezing weather coming, we always see the trucks out putting salt on the roads. A lot of times they try to do it before, right? So that once the temperature, of course, we're looking at Fahrenheit, right? At 32 degrees Fahrenheit, it would normally freeze. But if we get salt on the roads, it's got to get a lot colder before it freezes. So a safety thing there. Sometimes we will hear when you're cooking and you put salt in water, sometimes somebody will say, well, that'll make it cook faster. Do y'all see that theoretically, if you put sodium chloride in water, it's going to have to get hotter for it to boil? Now, if you did the calculation, it takes a whole lot of salt to make the water temperature go up. So really what we're doing is we're adding salt to the water for flavor. But I have heard people say, oh, it'll cook faster if you put salt in it. But we're talking not a whole lot faster. We're going to talk more about that and salt in the roads in just a minute, but let's move on to osmotic pressure before we work that last one. The formula for osmotic pressure, I gave it to you. That little pi stands for osmotic pressure. It's a pressure, so usually, y'all, you're looking at it in terms of atmospheres. Sometimes you might say millimeters of mercury, but it's atmospheres. Notice that M is a capital M. What does that M stand for? Molarity. R, what's R?
Constant.
It's the ideal gas constant. And y'all showed me earlier that you've used it enough, you kind of remember that it's 0.0821 liters times atmospheres per mole times Kelvin. And T is temperature. What kind of units does our temperature have to be in? It's going to have to be in Kelvin because of our units of R. Okay? What is osmotic pressure?
Is that?
Something to do with osmosis.
It does.
I was gonna say, the pressure at which it diffuses,
Well, it's to stop diffusion.
stop diffusion?
It's the pressure required to stop osmosis. Is she going to tell us what it is?
She probably might tell us the wrong answer.
Doesn't she do that all the time? Do you ever like say, you're so stupid? I do that all the time to Google. That is not what I asked. Okay. What's osmosis?
Diffusion of water.
Okay. In biology classes, we learn it's the diffusion of water. Why? Because that's the solvent in our body. It's all about water. But osmosis, y'all, it's the movement of solvent. Across a semi-permeable membrane. In chemistry, the solvent's not always water. In biology, it is. In plants, it is. I mean, that's still biology, I guess. Okay, so here's a little diagram of what goes on with osmosis. I have a U-shaped tube. Oops. Trying to make it uniform, but y'all just pretend I did. Right here in the tube, there's going to be a semi-permeable membrane. And y'all are familiar with that terminology, certainly in biology classes, that certain things cross membranes. It's not always solvent, though, right? Sometimes, I keep looking at you like you're a biology teacher to help me out, but it's physical science, wasn't it?
Earth science.
Earth science, same thing. So you have all the
I had
answers.
a biology
Okay.
endorsement,
Okay.
so
Okay, so you can answer all these questions.
technically I'm licensed to teach a biology class.
Okay.
I'm very thankful if they didn't put me in a biology class.
Oh. But in biology, you've got like your sodium and potassium. I don't want to say it too loud because I'm recording myself and I'll record myself wrong. Right? Sodium potassium pump? Isn't that a semi-permeable membrane? Okay, anyway. What we're going to put in this side of the tube, y'all, we're going to put water. Okay? And in the other side of the tube, I'm going to put sugar water. So I'm going to write sugar aqueous to show that it's sugar dissolved in water. Now, to be able to see the difference in these, the sugar would dissolve, y'all, but I'm going to draw little dots in it for the idea that there's sugar dissolved in there. Okay? So osmosis, I said it's the movement of solvent molecules across a semi-permeable membrane. Y'all, it always they move from the less concentrated to the more concentrated. Okay? So the way I think of it is, we've got water here, we've got sugar water here. The system wants both sides to be the same concentration. So in order to do that, what's going to happen is water is going to move that direction, water molecules, and it's trying to dilute that sugar so that there'll be equal concentrations on both sides. It can't dilute it enough, but y'all, what's going to happen is the water is going to cross the membrane. Do you see the level on the left side is going to decrease because water is going to move. And the level on the right side, the volume level, is going to increase. Now, there's going to come a point where osmosis stops because the difference between here and here, the solvent can't keep moving. This difference that stops osmosis, that's osmotic pressure, the pressure required to stop osmosis, when the difference in those two levels gets great enough. osmosis is why, y'all, when we eat salty foods, if we have a diet high in salt and we retain water, right, that's osmosis, your body hanging on to the water. Osmosis is what's going on, y'all, has everybody in here at some point cut up strawberries and sprinkled a little sugar on them and let them sit and they get juicy, right? Why do they get juicy? Because the strawberries start to release their juices because of the sugar, the really concentrated sugar that they're sitting in, and it makes for a really delicious dessert, right? Put some Cool Whip, whipping cream on there, yeah? Okay, osmotic pressure is important. Have y'all ever been hooked up to an IV? Okay, I mean, yeah or no, you know somebody that has. At some point in your life, you probably will be hooked up to an IV. It's very important that the IV solution is what we call isotonic. IV solution is isotonic with your blood. What does iso mean? Same. Iso means same, right? Isotope, same atom, different. Okay, isotonic with your blood. The IV solution and your blood have to have the same osmotic pressure. Because if they're not, what happens is if the IV solution is hypertonic, hyper means more. If it's more concentrated, yeah, well, if the IV solution is more concentrated, your red blood cells release water and they shrivel up. Okay? If it's high, what did I do? Hypotonic, they absorb the water and they pump. And one's called, because you know this, because I see, what's it called? Crenation? Oh, of your red blood cells. It's hemolysis. Hemolysis? Come on, y'all learn these terms, yeah? You have in a biology class somewhere, anatomy. Anyway, this was employed, y'all, when people would salt meats for curing them. The salt causes all the bacteria to shrivel up, okay, and then you can preserve the meat. I mean, we just maybe we know a little bit more about what's going on now, but I mean, that's what's going on. Osmosis. Who knew you'd be calculating? All right, so let's look at what we're given in the problem. How are we doing on time? We're great. Number 3. A 1 liter solution. There's a number there, so catch it. It's 1 liter solution containing 20 grams of hemoglobin. I'm going to abbreviate hemoglobin as HB. Has an osmotic pressure of 5.90 torr. The temperature is 22 degrees Celsius. And we want to calculate the molar mass of hemoglobin. Off the bat, I see we got to convert Celsius to Kelvin. Do y'all see that? All right. 22 Celsius is what Kelvin? It's 295 Kelvin. Okay, we also have to convert torr to atmospheres. I don't know if we've done that, have we? Okay, I'm gonna write at the top. There's 760 torr in 1 atmosphere. Here's your conversion. I'm going to write it in scientific notation, but you can do however you want to on that. I'm going to put 7.76 times 10 to the minus 3 atmospheres. Is that what y'all got when you divided it? Okay. Okay, let's look at, how do y'all want to set this up based on what we have here?
Try to find the molarity.
What's that? Say it again.
Try to find the molarity.
Okay, don't we have enough information that we can try to find the molarity? All right, let's do it. Tell me when y'all get to molarity. That's what I got over there on the right of the board. Okay? All right, so right now we can either, I'm not finished with it, of course. Do I need to wait? Or I'm ready to keep going unless somebody says wait or, okay? Y'all, the molarity of the solution is 3.21 times 10 to the minus 4 moles per liter. What was the volume of this solution? 1 liter. So do you guys agree that the molarity times the volume in liters will give me the moles? I have the molarity, 3.21 times 10 to the minus 4 moles per liter, times 1 liter. So don't I know that I have 3.21 times 10 to the minus 4 moles? Moles of what? Moles of hemoglobin. What am I trying to figure out? The molar mass. What's the units of molar mass? Grams per mole. So how are you going to figure out the molar mass of hemoglobin? It's the grams of hemoglobin divided by the moles of hemoglobin. Did you already do it?
No.
Okay, do you see?
I didn't realize we needed grades. It's in the problem.
Yes, it's in the problem. It's going to be a big number, y'all. Hemoglobin's it's a big thing. .23 times 10 to the 4 grams per mole. 62,300 for its molar mass.
And how are we getting there? Sorry, I was,
No, that's okay.
trying to figure out how, it was very minuscule, but I got 3.2. I feel like I typed in the exact same thing on my calculator.
Oh, but you got 2.0 instead of 2.1?
Yeah, well, I got 3.204.
Is this right? 3.2?
I got 205.
I never round until I get there.
And I typed in that exactly, 7.76 times 10 to the negative 3 divided by 0.0821 times 295. I don't know why there's a discrepancy between our calculators.
I tell you why. I didn't punch this number in. I took 5.9 divided by 760 and whatever that number was, I kept that number. That's what it is.
Okay, so now how are we getting to molar mass?
Okay,
I
so,
was
yes,
trying to
you're
figure out where I
there.
went wrong.
This is our molarity.
Okay.
We know the solution is 1 liter.
Okay.
So if we take, right here, the molarity, times the volume in liters, which is 1, that tells us our moles of hemoglobin. Then we came over here to do molar mass. The grams of hemoglobin it told us. The moles of hemoglobin we solved for. Grams divided by moles is molar mass.
So we're finding, okay, so we're multiplying molarity times volume to find moles.
Right.
And then grams divided by moles is the molar.
Okay? It's very common to use colligative property things to calculate the molar mass of something. That's a big use of colligative properties because it's easy to know that water freezes at a certain temperature and to put some kind of unknown in there, see what the temperature changes to, measure the change, and calculate the molar mass of your unknown. Okay, so that we'll do a lab like that in a few weeks. Now, y'all ready to listen? Just a little bit more? Because I'm not finished. Do we need a break? No? We good? Okay. I gave you the definition of colligative properties. If you look back, we said colligative properties, where is this? Way up there. Properties that depend on the number of solute particles in solution regardless of their nature. Well, we're ready to talk about what that means because I don't know about y'all, but based on what I've done so far, what does that definition have to do with what we've been doing? We've been calculating freezing points and boiling points. We haven't talked about the number of solute particles in solution. So let's talk about it. You actually already know the answer because you took Chem 1. Y'all remember doing electrolytes? Okay. I had a beaker up here, and I know that not everybody got to see my demo, but I had a beaker of water, and I put my electrodes in it, and the water would not light the bulb up. I don't know if y'all remember, I put sugar in it. Didn't turn the light bulb up. But when I put table salt in it, sodium chloride, it turned the light bulb up. Okay, so it goes back to that. So here's the deal. When I put, here we go, sugar is C12H22O11. When I put sugar in water, it dissolved, y'all, but it's a molecular compound, right? Molecular compounds, all nonmetals. Oh, I didn't mean to put solid. I mean to put aqueous. It dissolved as molecules. But when I put table salt in water, can you guys impress me with what you remember and tell me how table salt dissolved in water? Say again, Alexandria. Yeah? Yeah. Y'all, it ionized in solution, didn't it? That's what we said it did. So here's the deal. When you have an ionic compound, you took 1 mole of table salt and dissolved it in water. How many moles of stuff did we end up with over here? 2. When you put ionic compounds in solution, you end up with more molecules in solution. This is called the that's a T, Van't Hoff factor. What is the Van't Hoff factor for glucose? Sucrose at the top, sorry. Its Van't Hoff factor is 1 because it's a molecular compound. Okay? If you look at all these we've worked so far on this sheet, number 1 use glycerin. Look at number 1 on your sheet, C3H8O3. Y'all, that's a molecular compound. Its Van't Hoff was 1. Number 2 used what? Ethylene glycol, C2H6O2. Molecular compound, Van't Hoff was 1. Number 3 dealt with hemoglobin. It's a molecular compound, Van't Hoff was 1. So, what about, what's this? HNO3. What's the name of that? HNO3,
Nitric acid.
nitric acid. It's a strong acid. When you put it in water, it ionizes as hydrogen ions and nitrate ions. Do y'all remember doing this when we did net ionic equations? Your polyatomic ions stay polyatomic ions. What's nitric acid's Van 't Hoff factor? 2. Okay. What would the Van 't Hoff factor be for calcium chloride?
2.
3. Calcium ions and 2 chloride ions. Agreed? Because you got to balance it. There's 2 chlorides there. Van 't Hoff of 3. Okay? Sodium sulfate, what's its Van 't Hoff? 3. Because it's 2 sodium ions and sulfate ions. That's aqueous. I'm just not writing aqueous every time. Okay? Y'all, when they salt the roads, they actually put calcium chloride on the roads. It's not table salt. Calcium chloride's a salt because a salt is any substance formed from an acid and a base. Calcium hydroxide, hydrochloric acid. Calcium chloride's a salt. Why do they put calcium chloride on the roads instead of sodium chloride on the roads? Greater number of solute particles in solution is going to have a greater effect on the freezing point.
So just more atoms in general? Is that what it
Yes,
is?
more particles.
Part-
Yes, instead of atoms, we'll call it particles. More particles in solution. So here's how it works. I is the symbol for the Van 't Hoff factor. And realize we're talking about the number of solute particles in solution. There's been an I in every formula that we've used so far. In the freezing point depression formula, it's right there. I is equal to KF times M. It's just in the one we worked, I was 1. So I didn't tell you about it yet. It's in the boiling point elevation problem. Again, it was 1 in the one we worked. It's in the osmotic pressure problem. It's in the vapor pressure lowering problem, but it's in the mole fraction part of it. Because remember, the vapor pressure lowering was all about the solvent, and these are talking about solutes. So it's there, but it's just not in the front of it. Okay. Let's look at number 4. According to the Van 't Hoff factor, rank the following aqueous solutions in order from lowest freezing point to highest freezing point. So here's what we're going to do. We're going to say we've got let me just write them down. 0.050 molal calcium chloride, 0.15 molal sodium chloride, 0.10 molal hydrochloric acid, and 0.050 molal acetic acid. What's the Van 't Hoff for calcium chloride? 3. So 0.05 times 3 is what? 0.15? Okay. What's the Van 't Hoff of sodium chloride? 2. 0.15 times 2. 0.3. What's the Van 't Hoff of hydrochloric acid? That's 2 because it's a strong acid. 0.1 times 2 is 0.2. Acetic acid, that is not a strong acid. Do y'all remember me giving you a list of 7 strong acids in Chem 1? Acetic acid's a weak acid. Therefore, it does not have a Van 't Hoff of 2. It has a Van 't Hoff of 1.5. It's bigger than 1, but it's less than 2, so we're going with 1.5. So, what is that, 0.7? Yeah. You follow me? Okay, the question says, lowest freezing point to highest freezing point. Y'all, if we're looking at the freezing point problem, we know that delta TF is equal to KF times M. Each of these has a different molality. Each of these has a kind of different Van Hoff. But all of these have the same KF because they're all in water. And it doesn't matter what it is, but I think I remember that the KF for water was 1.86 earlier, wasn't it? So the KF's not changing. So do you see that the one that's going to freeze at the lowest temperature is going to be the one of these that this multiplication ended up being the highest number? That's going to be the lowest temperature. So 0.15 molar sodium chloride. Because it's freezing point depression, that one would lower it the most. That one's going to freeze lower than, what comes next? The HCl would come next. Then it would be the calcium chloride. And then last would be the acetic acid. Does that make sense? Let me ask you a different question. It's not on there, but let's ask. Which one of these four has the highest boiling point?
It would still be sodium chloride,
It's still the sodium chloride.
same order.
Because boiling point is elevation. So it's the same order for boiling point. This one boils the hottest, sodium chloride. Then HCl would be a little cooler, calcium chloride and acetic acid, because it's freezing point depression and it's boiling point elevation. Okay. I have another question for you. Look right here at our freezing point lineup. What if one of my solutions wasn't really a solution at all? What if I had pure water as a choice up there? What I want to know from y'all is, where does water fit into this hierarchy of freezing points?
Be the highest.
Tell me why.
If we're talking about freezing point depression, so all that's gonna be whatever the
Same
number ends up being.
Yeah, I'm on
Minus what you end up getting.
Water's gonna be here at this extreme. It's gonna be the highest freezing point, because all of these are in water. It's freezing point depression. Water freezes at 0 degrees Celsius. This 0.15 molal sodium chloride is gonna freeze at a much lower temperature than that. So the freezing point of water would be the highest of all these, because all these are in water and they're freezing point depression. Make sense?
Boiling would be below.
Boiling, water would still be here.
It'd still be there.
And then acetic acid will boil a little hotter, calcium chloride hotter still, HCl hotter still, and sodium chloride the hottest. Because it's boiling point elevation. Water boils at 100, all these boil above 100.
But we're going to highest, if we're, in order from lowest to highest.
That's freezing point right there. If we did boiling point, I changed what I said. Highest boiling point to lowest boiling point. I changed the words lowest and highest when I was talking about it. You had it right.